Hi all. In the previous video about turbulence modeling, we saw about how we derive Reynolds equations from the time averaging of Navier-Stokes equations. So we ended up with extra terms appearing in this right hand side. So these are termed as Reynolds stresses. So these expressions are termed as Reynolds stresses, and we face a problem of how to close these Reynolds stresses. How do we model these Reynolds stresses? Then the turbulence modeling is all about uh, how to make this make this Reynolds stress to have some kind of an constitutive relation similar to the law of viscosity. So we ended up with this kind of things. We using a Newton's law of viscosity, like how do we find a stress and strain relationship using some kind of viscosity proportionality constant is something related to viscosity. Similar analogy we put up in try to derive Reynolds stresses to relating it to the rate of strain rate of deformations. So there are many equations like we saw in the previous tutorial, like algebraic mixing length model, that we don't have any extra equations other than this Reynolds equations, and we analyze on dimensional point of view how do we relate try to identify the kinematic viscosity based on the velocity scale and the length scale of the turbulence. Then we closed and then relate then kinematic dynamic viscosity is identified from the dynamic viscosity. Then we entered into a velocity scale analogy to this one, and for similar finally we ended up with this relationship. And this has certain advantages as well as have certain disadvantage. One of the disadvantage would be that it couldn't able to capture the flows which has a large separation and recirculations. So to address that, there occurs another close-up model called K epsilon turbulence model. So this K epsilon turbulence model can address the issues which is occurring mainly because of the algebraic nature of the modeling the turbulent viscosity. So it takes into account of the dynamics of the turbulence. It means that turbulence properties, the Reynolds stresses are comes from the divergence terms. It can be transported by convection and diffusions, which that mixing length model lacks in capturing those kind of transport properties of the turbulence. So this nature of the dynamics of turbulence can be captured through this K epsilon turbulence model. For that, we try to formulate few analogies, like what does mean by instantaneous kinetic energy, how that instantaneous kinetic energy can be uh, formulated as a mean kinetic energy and fluctuating kinetic energy. The fluctuating kinetic energy is given by this one, and how this kinetic energy can be dissipated, that later will come to this part of this video. Now we comes into the rate of deformation tensor and the stress tensor. And again, similar to like kind of velocity components can be disintegrated into mean and fluctuating component, the rate of deformation tensor can be decomposed into a mean and the fluctuating component. And these are the final expressions for this rate of deformation expressed for the six rate of deformation x, x, y, y, and normal and shear components. And we can also see we wanted also have some mathematical things, like from numerical linear algebra, like how a matrix vector product can ended up. This is the matrix vector product and inner product, and it could be ended up in another vector, and the scalar product of the two tensor, how it would end up in a scale. So these are some of the notations that we needed to understand before going into the derivation of the k epsilon equation. One is for k is for the fluctuating kinetic energy, and epsilon will come to the part later of this video is called as rate of dissipation of that kinetic energy. First, we try to derive the equation for the mean kinetic energy. This is being achieved by for example, we know that in the previous video we have seen that how do we derive Reynolds equations. That equations is expressed in 3.12a to 3.12b, 3.12c. A for x component, B for y component, and C for z components. So we multiply this A component with respective x component of the velocity, namely u, and 3.12b is multiplied by the y component, respectively v, and 3.12c is for z component of the equation, which is multiplied again by the w. Once we multiply by this and adding up certain results and some good amount of algebraic manipulations, we ended up with time average equations governing the mean kinetic energy of the flow. So these have 7 terms. The 7 terms are expressed in this way: that first term is rate of change, transport by convections, transport by pressure, transport by viscous stresses, transport by Reynolds stresses, and it's like kind of a source and sink components. It's a dissipation and the turbulence production due to the turbulence. So again, based on the properties of these terms, we can aggregate into a commonality. That 3, 4, 5 are aggregated based on certain commonality because the appearance of the divergence terms. Again, the term 4 and 6 are being aggregated because this is related to the viscous effects. And the sixth one and seventh one are something related to the turbulence, which is one is for dissipation and one is for the productions. So we similarly, how do we derive for mean kinetic energy? Similarly, can be derived for the equation for the turbulent kinetic energy. This is again we have equation for Navier-Stokes 3.98 to C. This is again we can multiply by the respective fluctuating component u dash, v dash, and w dash. Again, we will be following the repeating the same process for the Reynolds equations, like I mentioned in the mean kinetic energy 3.1 to A, B, and C, multiplying with the respective components, and we add all these resulting these two equations and making some a fair amount of rearrangements can end up with this again this kinetic energy, which have again these 7 terms, and that is for convections, pressure, viscous stresses, and now stresses. Similar, this is exactly similar. The terms are exactly similar analogy to the mean kinetic energy. That's what it says here. One good thing is, if you see the 7th term in both equations, they have equal in magnitude but opposite in sign. What does it mean is, the mean kinetic energy is extracted into into a turbulent kinetic. There is a conversions, that how this kinetic this turbulent kinetic energy is produced because the way that large eddies extract those energies from the mean flow. That is what it means, the change in sign in the 7th term. This is, so there it will be a positive sign, here it's a negative sign, because that's where that values have been extracted from that equation to this equations. Similarly, we can have viscous dissipation terms in the 5th term, which has some negative contributions, and this is called as some of that these are dissipating, and this kinetic energy is dissipated into some kind of due to the main how that large eddy is bringing those energy into this kinetic energy. These are similarly as small eddies again take those energies from the mean this fluctuating kinetic energy into some viscous thermal effects. So that is being captured as this one is called as epsilon value. This is called as viscous dissipations. So now we try to derive the expression for the kinetic turbulent viscosity mu t based on the characteristic dimensional analysis. So velocity in the previous mixing length, as per we can express in terms of kinetic energy and the dissipations. So the reason for this small scale effect putting into the large scale is how those energy cascades are related. So that's the reason, the main reason that epsilon is being added into the characteristic length scale of the large eddies. So based on this analogy, we again, like similar to the mixing length model, we have these expressions, and that expressions using this expressions, we substitute this expression, and we finally ended up with the turbulent viscosity in expressions of fluctuating kinetic energy and viscous dissipations, and mu is a so we have finally two equations for k and epsilon, that is 3.35 and 3.36, And these 3 points similar like kind of a convection diffusion equations and source and sink terms. In this convection diffusions and source and sink terms both have, and together these two equations have five uh, empirical constants, and those empirical constants are done from extensive experimental analysis. We could people identify that these are some kind of nominal values that could be used for wide range of flows. So this is all about K epsilon turbulence model, and these are some of the things how we ended up with other terms like kind of how we model the Reynolds stresses using this K epsilon value. This mixing length model, if you see that they don't have these additional terms, but this is have an additional term, because when this all the stresses are added, this will become zero, but in here that it ended up with non-zero values, and it gives some physical reality. The boundary condition is like inlet, outlet, and wall boundary condition, free stream boundary conditions can be approximated through these expressions. This is have a Newman boundary conditions, and these are value. Only the things the inlet distribution of K epsilon value has to be given, but in reality we don't know that. There will be some fair amount of assumptions by which we can identify this distribution of K and epsilon for the inlet flow using this kind of expressions. So hopefully in next video we will see about how this specialized case of high Reynolds number, how the standardized K epsilon model can be altered and be tuned for the high Reynolds number flows. Thank you.